Okay, we're going to continue our discussion on analyzing power functions. The next set of power functions that we are going to work on, we're familiar with as well. These power functions are called inverse power functions, and you can see how they're writing those inverse power functions. We've noticed, and we've had these just prior to this, a butterfly graph is kind of what we talk about, the shape of that graph. So we're going to look at butterfly graphs, and the other inverse power function that we haven't seen for a little while is our volcano graph, which they're going to write as x to the negative 2 to fit into this power model concept. If you remember, our power model concept said f at x had to equal a times x to a power of n. So we're looking at powers of n that are now negative. So we're looking at negative 1, we're looking at negative 2. There's a nice little pattern that develops here. Anytime that power is a negative odd, then it's going to be in the shape of a butterfly graph. Anytime it's a negative even, it's going to be in the shape of a volcano graph. And these are things that we've studied before. So we're going to work with a couple of ideas here and trying to keep you guys straight with your negative exponent rule. If you have f at x equals x to the negative 2, remember that the negative exponent reciprocates your base. So really I have on the base before I begin anything is x over 1 raised to negative 2. If I use my negative exponent rule and reciprocate the base, it's now 1 over x raised to the second. And then that is equal to 1 over x squared, because 1 squared is 1 and x times x is x squared. So you're going to have to go in and out of this negative exponent idea and relate it back to, maybe it's a little bit easier for you to think of it as 1 over x squared. It doesn't matter that these two things are equivalent to each other. It's just a matter of formatting. How do you want to write that equation? So we're looking at reciprocal functions. Again, I think we've talked about these as inverse power models through our experiences with core. We call them the inverse power model because whenever we deal with these numbers, large numbers become small, small numbers become large. We'll look at some different features of these graphs as well. So like I did last time, we're going to go into a little bit of just graphing some of these power models, these inverse power models that is. And I'm just trying to find them where I had these listed. Okay, here's the first graph. This should be y equals 1 over x, or y equals x to the negative 1. And the first thing I want to illustrate to you, when I click on this, on that, and it's highlighted, this program is going to graph that function. So when I click on that, it's going to change the color, but it's not going to change the path of it. I'm just showing you with this strategy here that these two are equivalent forms of the exact same equation. So as I come back here and I click graph it again, changes color, it's saying, hey, that's the same graph as what you had before. It's just a change in format. So we have this negative 1 or 1 over x. The other graph I wanted to point out to you right away is y equals x to the negative 2. If we graph y equals x to the negative 2, it should be the same shape as the graph I have here. I must have deselected, so I go graph it again and grab it. Now I'm going to graph it, and you'll see that that red graph is going to get turned to a different color, which it did. So I go and grab the equivalent form 1 over x squared, and again here comes our volcano graph, exactly the same location it was before. So just keep in mind we can write them in different formats, and really we're looking at two different forms of or shapes of a graph. One is a butterfly, the other one is a volcano. Okay, so let's take a look at some changes in our graph as this exponent becomes bigger. Now I've written them as y equals 1 over x to the third, or we could write it as y equals x to the negative 3. I'm going to go back to our parent function graph. This is the graph of y equals 1 over x. So what's going to happen when we graph y equals 1 over x cubed? Now keep in mind these are called inverse function graphs, so whatever we learned last time about our power models, when we had positive even and positive odd powers, things are going to behave a little bit different because of this 1 over concept. So I'm going to graph y equals 1 over x to the fifth, and we're going to compare that to the 1/3. So here comes our new graph. This is the graph of y equals 1 over x to the fifth, the one in red, which is also y equals x to the negative 5. So what is happening now? So again, one of the nice points to track, and it's the same point that we had before, is the ordered pair 1, 1. You notice that our graphs cross at that, which means they got the same input and output values. So we put in a 1 and raise it to the fifth power, it's 1, and 1 over 1 is 1. So at 1, they're exactly the same, and at negative 1, they're exactly the same. But now how did our graph change? Okay, so on these, it looks like on the inside, it actually is getting steeper. So from a negative 1 to 1, as we change these inputs, now I'm going to take this 1/2 again, a nice convenient number of a half, and we take 1/2 and we raise it to the third power. We get an output of 1/8. That is incorrect. Let me try that again because I have a reciprocal function. It's 1 over 1/2 raised to the third power, okay, which is going to be 1 over 1/8, which is equivalent to 1 divided by 1/8, which is equivalent to 1 times 8, which is 8. Now what happens when we choose or use our other function, which is 1 over, take our input value of a half, raise it to the fifth power. This is 1 over 32, which is equivalent to 1 divided by 1 over 32, which is equivalent to 1 times the reciprocal, which is 32 over 1, or 32. So as we get inside, as we reciprocate our fraction that's on the bottom, it actually becomes large. So inside, between a negative 1 and 1, our graph now becomes steep, or steeper, which is just the opposite of what happened on our other graphs. When we looked at our original power models, the ones with the positive values of 2 and 3, on the inside it became flatter, on the outside it was steeper. So it's kind of nice because it's called an inverse power model. All the things that we learned on the previous one gets flipped around because it's inverse. Now on the outside of our graph, it becomes flatter. So these are flatter on the outside, steeper on the inside. One of the things that's kind of nice to always kind of take a look at is how is this shape of the graph being pulled? Is it being pulled away from the origin? So I'm looking at the origin. Is our new graph being pulled away, the center of the graph, or is it being pulled towards? And as this gets bigger and bigger, you're going to see it pull away even farther when we get to higher powers. And I thought I had a higher power here that we could look at. So I'm going to try to grab 1 over x to the 7th, which I had at one point in here. Okay, I don't see it, but I can type it in there quick. So I'm going to graph y equals, and then 1 over x raised to the 7th. Okay, I'm going to take that and move that up here so I keep it with my other graphs. I'm still not there. Here it is. I drop it in there. We're going to go back and we're going to graph it on our other two graphs. Remember, the green was 1 over x cubed. The red was 1 over x to the 5th. And here comes 1 over x to the 7th. Okay? Change colors on it so it's a little bit more distinctive. Then there's our blue graph. Our blue graph is y equals 1 over x to the 7th. Keep in mind, what's happening on the inside from a negative 1 to 1 is it's going to get steeper, because as we reciprocate those smaller and smaller fractions, the number actually gets larger. That's where the term inverse comes in. And on the outside, it's getting flatter. It's getting closer and closer to your horizontal asymptote, where y is equal to 0. So just the nature of our graphs for butterfly graphs. Now that's if our power is odd. I'm going to clear ink and we're going to take a look at some of our even powered graphs. So we're going to go back to our basic even powered graph, our inverse power that's even, which is our volcano graph. So this is y equals 1 over x squared. We're just observing our graph. If it's squared, one of the nice things to kind of remember about 1 over x squared, no matter what your input is, if you square it, it's going to be positive. So if you notice, the graph is no longer a butterfly graph. A butterfly, what used to be a butterfly, has now been reflected up over the x-axis. Because it can't be negative, it's got to get flipped upwards, so all the outputs are positive. So that's kind of the difference between a squared versus an odd power versus an even power graph. So that was our x squared. Let's take a look at some other members of this family. 1 over x to the 4th. I'm going to graph that on the same set of axes. And do you see the same phenomena happening here on the inside between 1 and -1? It's getting steeper. On the outside, it's getting flatter. That kind of a yellow, mustard-colored yellow graph is steeper on the inside, wider on the outside. And that was our x to the 4th. We can look at one other one just to give you one more example of what's going on with these inverse power models. On all even powers, you're going to see a volcano graph. The larger the power becomes, the steeper it gets on the inside between -1 and 1, and the flatter it gets on the outside. And you can run the numbers on this and pick values, and you can see how these numbers are increasing faster and faster. So rate of change is great between -1 and 1. It's rather slow on the outside. So what I want to do is have that discussion about what these two graphs look like. Again, it really boils down to two different looks. We either have a butterfly graph or we have a volcano graph. The nice thing is we have had some experience with these. We haven't had a lot, but we've had some exposure. So let's take a look at our guided practice problems. Again, we're going to analyze each function, describe domain range, intercepts, end behavior, continuity, and where the function is increasing or decreasing. The reason I kind of like to rewrite these is I want to see this in a little different nature. It's a -1/2. And since it's x to the -4, I can rewrite that as 1 over x raised to the 4th, which I think that's probably not a bad way, but I think I want one more adjustment to it. I want to write that as -1/2 times 1 over x to the 4th. Because now I got this thing pegged in my mind. This is the inverse power model raised to an even power, so it has to be the shape of a volcano. And that's what I graphed here in the first graph I'm showing you. This is, to me, the parent function graph of x to the -4, or 1 over x to the 4th. Now there are some different variations that we just modified it. We modified it by doing, number 1, a reflection about the x-axis. So our volcano doesn't go upward, it comes downward. The second thing that we did is we multiplied it by 1/2 on the outside of the grouping symbol. So that is a vertical adjustment. Now the adjustment that we made vertically, if you multiply by 1/2, or any number between 0 and 1, that's going to make our graph compress towards the x-axis rather than stretch. So we're going to track the point. This ordered pair 1, 1. When we put in a 1, we get a 1 back out in our parent function graph, 1 over x to the 4th. But now what we want to do is take all of these outputs and we're going to multiply them by 1/2. So take 1/2 of all of these 1 over x to the 4th. But when we put in a 1, we got a 1, we got to take 1/2 of it. So when we put in a positive 1, we get a -1/2. And again, it's a little bit hard just because of the axes, but a little bit limited on what I can show you on this slide. So our order pair, 1, -1/2. Remember, it was going to be 1/2, but we reflected it, so it was going to be coming downward. So a little bit of discussion about what's happening to the graph. We're trying to tie it into what we learned last unit, which is about vertical stretch and shrinks, reflections across the x-axis and y-axis. All those things you learned about transformation still are going to apply in our power model graphs. So okay, let's talk about the issues here that they want us to discuss. First of all, they wanted us to take a look at this graph, and we're supposed to describe its domain. Okay. I had that rule rewritten in a different form for another purpose, and then I erased it, so I'm going to put it back up there. It's 1 over x to the 4th. The reason I want it written like this, we've been practicing for quite a while domain restrictions, and there are two clear places that we really have to be careful on domains. Number 1, we never want to divide by 0, and that's what I'm looking at here. If I rewrite this, I'm probably more inclined to remember that I can't divide by 0, so I know that x cannot equal 0 in this problem. If we have 0 in for x, it is undefined since division by 0 is undefined. So that is why what you're seeing here, and we've been familiar with this vertical asymptote, the line that it can't touch, and that's when x is equal to 0. So when you start seeing gaps in your graph, number 1, that should be a red flag graphically when you see gaps, that there's a restriction on the domain. That comes back up here to our algebraic rule. Of course there's a restriction on the domain because we can't divide by 0. It's fairly apparent when we rewrite it this way. So let's talk about the domain and describe it. We know that it can be all real numbers except 0. Last time I wrote it in interval notation. If I stay in that same theme, our domain is going to be all real numbers except 0. It goes from -infinity to 0. Put a parenthesis because we do not want to include it. We want to union that with 0 to +infinity. So that's our domain. Next thing we're going to do is we're going to look at the range. Okay. In order to find the range, what I want to do is I want to look vertically. I want to look up and down the y-axis and see, is there any value that y can't get to, or what is the maximum value, what is the minimum value, are there any limitations to it? And in this case, what we're seeing is a horizontal asymptote here at y equals 0. So there is a cap on how big the y's can get. They can get close to, but they can't touch 0. So in our range, we want to list all numbers that go from negative infinity all the way up to 0, but not including 0, because they're going to go down to negative infinity, but they won't touch that horizontal asymptote. So our domain and range are described as such. The intercepts. If we look at the intercepts, or we look at our graph, there are no places where our graph can touch either the x or the y-axis, because that's where we have our vertical and horizontal asymptotes. So in this one, on the intercepts, there are no intercepts. End behavior. Again, when you start talking about end behavior, just write down your strategy. I'm going to see what happens as x approaches a positive infinity. Where are the y values going? So as x approaches a positive infinity, the y values seem to be coming up and getting closer and closer to 0. How about when x approaches a negative infinity? Well, the same thing's occurring here. As x's get bigger and bigger, as we go to the edge of this graph, our graph is actually getting closer and closer to the x-axis once again. That means y's are approaching 0. So our end behavior on this is going towards 0. Again, I'll put a little plug into what we learned last year. What we have is a power model that says negative 1/2 times 1 over x to the 4th. If we rewrote this whole thing, it's negative 1 all over 2x to the 4th. The top is a degree 0, so we're talking about degrees. That's a degree 0 over a degree 4. If the bottom had a bigger degree than the top, that meant the dominant term is going to grow faster. When the bottom grows faster, the denominator grows faster, our entire fraction gets closer and closer to 0. So we do have some ways that we did this algebraically as well, as far as describing end behavior as well. So next thing, continuity. We can definitely tell that our graph is not continuous everywhere. We know that there's going to be a break in it. When we're talking about continuity, look left and right in your graph. It's almost like looking at your domain. Our continuity test on this one, we view our graph. We're going to have a hole in our graph. Our hole is going to occur at x equals 0. So as far as our continuity, is continuous everywhere except at 0. So when we list our continuity, it can go from negative infinity all the way to 0, union 0 to infinity. Continuity. Where are there any gaps, any breaks in your graph? And finally, increasing or decreasing. Keep in mind, we want to be very consistent in our strategy and method here. We want to look at a graph from left to right. So as we have our x values go from the left to the right, as they get larger, what's happening to our graph? Well, then our graph is going downhill. If it's going downhill, it's decreasing. So our graph is decreasing from negative infinity all the way up to 0. Okay, so now what happens once we hit that vertical asymptote? We hit that. Now our graph, reading it from left to right still, what happens is our x started getting bigger than 0. Now our graph is on the uphill climb. So because our graph is going upward, our graph is increasing on the interval from 0 to positive infinity. So we have a little bit of a graph that sometimes is hard for people to interpret. They don't read it from left to right as conscientiously as they should. Always read from left to right. That'll tell you increasing and decreasing. Okay, so that's our first example, 2A. Now let's take a look at 2B. 2B, what I like to think of, our parent function for this one would be 1 over x to the 3rd, because it's an odd power in the denominator. Inverse power model that is odd, it's going to be a butterfly graph, and that's what I'm showing you here. This is the parent function of 1 over x cubed. So now we start applying the strategy of transformations. What about this for? What does it do to your graph? Well, anytime we multiply by a value bigger than 1, it should be stretching our graph. Now, take a look at our point that we like to track. The ordered pair 1, 1 is on all reciprocal functions. So now what we want to do to our 1 over x cubed graph, we take all of those outputs and we want to take them all and multiply them by 4. So the only change is when we put an input of 1, we should have an output of 4, and it looks like that point is on our graph. And also, if we put a negative 1, we should get back to a negative 4. Where we had a negative 1 was a negative 1 for an output. So we can see the stretching of our graph. These inverse power models between a negative 1 and 1, they get stretched farther and farther away as the power goes from 3 to 5 to 7. So all right, let's have our discussion about the domain and range. For our domain, I want to search the x-axis. Are there any breaks in this? Wherever I see a break in the graph along the x-axis, I have to be thinking about some type of domain restriction. Again, this is 4 over x cubed, never divide by 0, so that means our domain is all real numbers except 0. So don't include it, union it with 0 to infinity. The range. Now the range is a little trickier because we got this thing going all the way from 0, almost 0, never touching, but going down to negative infinity. On the other side, we got it almost 0, but going towards positive infinity. So we get all real numbers except 0. So as I've done before, what I do is I look up and down the y-axis and I see, is there any breaks in our graph along the y-axis? So as I'm viewing that, I'm seeing a gap right along the x-axis, and that's when y is 0. So go from negative infinity to 0, union, 0 to positive infinity. Domain range. Intercepts. Because we have our vertical and horizontal asymptotes sitting right on the x and y axis, there are no intercepts again. Next thing, end behavior. What happens as x approaches positive infinity? As x approaches positive infinity, our y's are coming down, flattening out, and they're approaching 0. Put 0 in there. And as x approaches negative infinity, what does y do? So as y approaches the negative infinity, or as x approaches negative infinity, y is approaching 0 again. So it doesn't matter. What you could do if you like, you could say as x approaches both the positive and the negative infinity, y approaches 0. And you can write that as a compound statement, and that shortens it up a little bit when you see that the same end behavior is occurring. Next thing, continuity. We already have discussed where we have vertical asymptotes, so as we look along the x-axis, there's a gap in our continuity right here at y or x equals 0. So it's continuous on the entire range. So we're talking about our continuity. It's continuous on the set from negative infinity all the way up to 0. Union 0 to infinity. As you see, some of these things get a little bit repetitive. And where is the function increasing or decreasing? So let's take a look at our graph. Let's feed it from left to right. As we go from the left to the right, as our x's get bigger, our graph is going downhill. So it's decreasing on the range from, or on the interval from, negative infinity all the way up to, but not including 0. Okay, what happens as we come across the vertical asymptote? X's are getting bigger. As x's are getting bigger, what's happening to your graph? Once again, your graph is going downward, so it's decreasing again on another interval, or from 0 to infinity. So where is it increasing? Never. This graph is never increasing. It's always on the fall, no matter where you go from left to right. So that concludes the second set of examples. These were on butterfly graphs and volcano graphs and getting familiar with those parent functions and their members of their family. So quick review on those.